Welcome back to your Theory 1. Okay, so we will now proceed with your Module 5. This is the influence lines on statically determinate structures. Okay, so what is influence line? So let's first try to define what is influence line. Okay, so if we say influence lines, this is a graph of a response function of a structure as a function of the position of a downward unit load moving across the structure. So actually, if we will try to understand this definition of influence line, we are actually just talking about the outline, okay, the outline of the effect of a variable load. So if we will try to read this next paragraph, it says there that the concept of influence line is very important in the analysis of structures due to variable loads. Since what we had before in our previous modules, we had there the dead loads or the permanent loads. Say permanent loads, it will not change with respect to time. Okay, so that will be applied in that position to be considered for the analysis of the structure. However, if we are talking about variable loads, that is now varying or that is now changing with respect to time. So actually, one example of that is your live loads. And so your lateral loads, just like the wind loads and then the earthquake loads, these are variable loads. Okay, so since that is changing with respect to time, and if we are designing a structure, we want to get the maximum effect of that. And then how are we going to analyze that one? Okay, we are not going to locate or we are not going to put that load on each position and analyze it one by one. Rather, we are going to analyze the effect of that as a whole. Okay, or as a function of time, or as a function of time at the same time as a function of distance or the location itself of the load on the structure. So we are going to represent that single or that outline as a graph. Okay, so that is what we call the influence line. The influence line. So the variability of the response of structure, if we say response of a structure, that is just simply talking about the reaction, or it could be we are talking about the reaction, or it could be the internal reactions. Those are the shear and the moment, internal shear and the internal moment. Or we could also be talking about the deflection. So those are the response of structure that we are talking about. So the variability of that response of structure with respect to the position of load is outlined using this influence line. So for example, okay, let's try to consider the simply supported beam AB, and let's say that's a load P, concentrated load P, which is at a distance x, since we can say that that is moving. Okay, let's say that is moving. So at a certain time, that's at a location x from the, let's consider a fixed point, let's say A. At a certain time, that is a distance x from the fixed point or from the reference point. And then another time, or since that is again changing, that is moving, so at a different time, that will have a different distance x. So again, that makes it variable. And due to that position of that with respect, of course, to the orientation or to the structure itself, that will give different reactions. If we are talking about reaction, it will give different internal and shear and moment with respect to a single point we are considering, or different deflection. Again, so that depends on the location. So how are we going to outline this one? We are going to outline the effect of that variable load to this structure using this influence line. So this is an example of that. That will be a line. Okay, that's actually just a line platted. Okay, which is platted on the x and y. However, our x and y will now become the variables. Wherein the variable there is of course the position. Okay, let's put that one as x, the same as the x-axis. Let's try to put that as the abscissa. And then the other variable there is the response we are considering. So if we are talking about the reaction at A, vertical reaction at A, then the other variable being affected by that position is the AB. Okay, so we will plot that one in the vertical and horizontal axis, wherein your ordinate is the response, and then your abscissa is the position or the distance to a certain fixed point. So that is how we are going to outline the effect of that. So how we are going to interpret this one is that at a certain distance, of course, that is now referring to the distance from, let's say you choose your A to be the reference point. At a certain distance, we can actually read a value using this line. Of course, this is the line graph. you can now read, let's say, at a certain distance within this part, let's say that is 5 meters, let's say that is 5 meters, that is the value here on the x-axis. Then you are going to read using the line graph, okay, that you drew, that is the influence line. You can now read the AB. It means that is the reaction at the vertical of A due to that load at a distance x, at that distance 5 meters from A. If you want to get another another position, let's say at 10 meters, move on to the 10 meters of that, read again the ordinate of that, and that will be the response, that is the vertical reaction when the P load is located at 10 meters. Okay, so that is how we are going to outline the effect of a variable load on the structure. Okay, so influence line. So this is the procedure. So first is, since again, if we are talking about load P, that could be different. Okay, it could be 50 kip, that could be 100 kip, and so on and so forth. So let's just to make it simpler, okay, to make it simpler, instead of substituting or considering that, let's say that is a very complicated number. Let's say you want to use the exact, that is a decimal. Okay, it will be a little bit tedious for us to be repeating or to be carrying that complicated decimal point, or if you want again the exact value. So rather, you will be using a unit load. If you see unit load, let's say you are in kilonewtons, then use 1 kilonewton to draw your influence line. So that's it. So that is the first step. Consider a unit load with a distance x from a chosen reference point. So first and foremost, you need to choose a reference point. Okay. That is where we will locate the distance x, since again x is a variable, since that is changing. And then below we will consider not the exact value or not the actual value, rather we will consider a unit load, so that, okay, so that your graph will be general, your influence line will be general, because there might be a time that P will now change. Instead of, let's say, originally that's 25, that will now become 50, or that will become 200. So from time to time your load P is changing. You can actually still use the influence line that you draw using the unit load. Okay, so we are going to draw the influence line using the unit load. Later on, okay, we will discuss how to calculate the actual effect of the actual load, okay, using the influence line of a unit load. So now, second there is, once you, all you need to do is locate a unit load somewhere there, okay, and then try to reference your distance from a fixed point and call that one as distance x, since that is variable. And second is to establish the response equation as a function of distance x. If you say response equation, let's say you are after the response of reaction or a reaction response. So for example, in here, your response is the vertical reaction. Okay. So you are going to establish the equation, since of course that will be in terms of an equation. You cannot solve an exact value since this P is moving at a certain variable x. So of course that will be affected. So as that moves, as x changes, that AB also changes. So this response is a function of the distance x, or a function of your position x. Therefore, we are going to establish that by, of course, using equilibrium. Of course, summation vertical, and so on and so forth, summation moment, and so on and so forth. So that is how we are going to establish the response equation. Now we have that response equation, or all we need to do is draw the diagram of that. If we say diagram, we are talking about the line graph of that, okay? Since we are talking about influence line, using the equation that we established here on the second step, we are going to plot that one on the x and y, or in the abscissa and the ordinate, wherein your ordinate is the response. Okay, again, response. If you are talking about now, if you are focusing on deflection, that is your response. Then your abscissa will be the distance or your position x from a reference point. Okay, so again, all you need to do is assume a unit load, indicate the distance x from a reference point, and after that, you will establish the equation of the response, and then draw the diagram or the line graph of this response with respect to the ordinate as your response, or your response as the ordinate, and then the distance x as the abscissa. Now you have already the influence line. Now, since as I mentioned a while ago, we are going to draw the influence line using a unit load. Why? To make it general. Okay, in general, so that you can change the value of the load if you want to. So how to calculate now the effect of the actual load is, of course, for us to use the actual load itself. So to calculate the actual value of the response, multiply the load intensity. If you say load intensity, that is the actual value of the load with the corresponding ordinate of the influence line. Okay, so again, let's say you use unit load to draw this influence line here for AB. Then, if you want to get, or if you want to read the reaction AB at 5 meters, all you need to do is read the ordinate in your unit load influence line at 5 meters. But that is not the value because that is due to unit load. So all you need to do is multiply that unit load ordinate by the actual value of the load. So actually that is a superposition theorem. Okay. As you increase the load, the effect also increases. That is proportional. That's why we can actually use this 2+1 superposition. All you need to do is assume a 1 unit load, and then if you want to get the value of the actual, all you need to do is multiply by how much, okay, to that unit load. So that is what is the reason again? To make it general, so that you can change the load from time to time if you want to. Okay, so that is influence line, and that is how to calculate the actual response using the unit load. The influence line using unit load. Okay, so let's start with unit 1. This is the influence lines for beams in frames. Okay, so we will be dealing with the analysis of beams in frames due to the variable loads. Okay, so that is using influence lines. So, by the way, another important application of the influence line is for us to locate the position. Okay. Let's go back again to the simple figure. So again, if you want, let's say you want to know where should be the load P located for us to get the maximum, let's say, reaction at A, your AB. So you can actually figure that out in your influence line. Since influence line outline, okay, that influence line outlined the entire effect as the load P crosses the entire structure, then you can actually use that to figure out which one gives us the maximum response. So in this example, you can see the maximum as the, of course, the biggest or the largest ordinate. That is the maximum effect or the maximum response. So we can say that we will have that maximum AB if your P is at the A itself, at the point A itself. Okay, that is the maximum given this influence line. Okay, so it means that the reaction at A, vertical reaction at A, is maximum if that P is exactly on top of that A or on top of that support, and that will be 0. Okay, as you can see here, that will be 0 if your load is exactly on top of B, because of course your B will now try to catch or will receive the entire force P. Therefore, your reaction A that we are focusing will have no effect, or there is no effect on that reaction. So again, that is the importance of influence line. We cannot actually predict that one by merely looking at the figure. Yes, there will be a time that, for example, if we are talking of reaction, you can just say that that is the maximum if P is concentrated on the top. But if you are now talking about the deflection, especially if you have more than one member, okay, or you have more than one segment of the beam, there are more reaction on that within the beam, it is hard for us to figure out in which location the load P should be applied to get the maximum reaction or to get the maximum internal shear or moment or even deflection. So again, that is because it is a variable load. Unlike, of course, in your dead load or in your permanent load, we can actually make use of the equation. Actually, you can make use of the equation, but you need still to establish the response equation, and then of course that is now using the calculus maxima minima. Okay, so that without even drawing, you will now actually use the equation by using the of course using the concept of the maxima minima in calculus. However, if you are not if you are not that good with this application of maxima minima, rather use the influence line. All you need to do is plot that one as a line. It is simple for us to draw the line. Okay, that's it. Figuring out or locating the location of the force P for the response to be maximum. That is one important. Okay, that is one important use of the influence line. So in this unit 1, okay, beams and frames, we are going to draw influence line of beams and frames, and then of course calculate the actual response using that influence line that we will be drawing in beams and frames. Okay, so let's try to have example to discuss this application of influence line in beams and frames. Okay, so for this example, it says there, draw the influence lines for the vertical reaction at C. Okay, so that is one response that we are going to analyze. Okay, and then the internal moment at B. So as you can see, this is the figure. We have your point A, point B, point C. For in your point B is the midway, or that is the middle of point A and C. Okay, and then that's it. We are going to focus on analyzing the effect or the effect of the moving loads at the vertical reaction at C. So that's it. Let's say that is CV. So that is one of the response that we need to analyze. Okay, we need to study. And then second is the internal moment at B. So we will be trying to cut this at point B to expose that internal moment, and then of course establish also again an equation of that moment, internal moment due to the moving load, and then we will be having another influence line for that. So we will be expecting two influence line for CV, vertical reaction at C, and then influence line for the internal moment at B. So later on we will cut that one. And then after that, determine the maximum response. Okay, so that is now what I'm mentioning a while ago. The use of the influence line is to figure out the maximum response, and at the same time, of course, the location. Okay, so maximum response due to a moving load of 50 kips using the influence line that we will be drawing. Okay, so we will be solving for, we will be ending up with 4 results, 2 influence line, and then 2 maximum. The maximum of that CV, and then the maximum of that internal moment at B. Okay, so first, this is our figure. So as you can see, we have here 2 supports, vertical, horizontal, and then vertical, 3, and then another vertical. This is a ruler. So we have here 4. So actually that is, if you are considering it as entire figure, that is first degree. Externally indeterminate first degree. However, due to the presence of the hinge there, that will be additional equation in addition to the 3 equations of equilibrium. So we will be having 4 equations with 4 unknowns that makes it determinate structure. Okay, so now if that is determinate structure, then actually you can just use the equilibrium equations. So first is, let's try to start with the CV. Okay, and again, going back to the steps, first is to consider a unit load at a distance x from a chosen reference point, and then second is to establish the equation for that response, and then draw that equation, draw the diagram of that equation for us to have the influence line. Okay, so again, let's try to focus first on the vertical reaction at C. Let's call that one as CV. However, for us to calculate the CV, we need to first step 1 is to assume a unit load. So let's say that is 1 kip at that location at a distance x. Let me choose A as my reference point. So every distance x will be referred to from A. Okay, even if that is on this segment CD or segment DE. However, okay, I gave you already a little bit complicated example for us to outline the entire concept within one example. Okay, so that will not be having more than one, since that will be making our video longer. So again, as you can see, if we will try to calculate that CV, the equation of that, considering your member DE, okay, considering your member DE, because actually we cannot calculate directly the value of CV, okay, since again there are 3 unknowns, and we will subtract, or we will remove the summation of moment, the summation of force is horizontal, since we do not care about the horizontal reaction, since again we are focusing on the verticals at C. So for us to get the vertical at C, there is a relationship with AB and EB. So we really need to solve AB or EB. Okay, for us to solve that CB, unless there is other way for you to solve directly the equation of CB. Okay, however, we cannot do that because if you want to summate vertical, there will be three unknowns, AB, CB, and EB. If you want to take a moment at A, you will be exposing 2. If you want to take a moment at E, the same, you will be exposing 2. So we cannot go directly to CB. So we need to pass through one equation. So it's either solve EB and then AB before solving CB. So actually, since there's a hinge there, that is, again, if we say hinge, it is free to rotate at that point. So there is no moment reaction. There is no internal moment at that point of the beam. It means it is free to rotate at that point. So if I am going to detach this pin, the summation of moment at that point D should be 0, the left side or right side. So we will try to separate, okay, separate this one, detach the hinge, and then consider the member DE, okay, and then, okay, since we are referring here to variable x, again, we need to be careful, just like in your double integration, okay, determining the deflection using the double integration, you need to establish equation in terms of x and it. However, as x passes another force, okay, or as the x surpasses another force, there will be additional force to be considered. So we need to divide actually into segments. Okay, so first is from 0 to 40. Actually, as this one kip goes from A to D, it will not affect or it will not change the equation of CB. We will later on figure that out. But as that goes beyond your point D, beyond the hinge, you will have a different, you will be having a different equation. So first, I will be considering from 0 to 40, when x is from A to D. Okay, if that's the case, okay, it means that your one kip is not yet there. Okay, since we are focusing, let's try to focus ourselves on your member DE. Your member DE. So when x is still from 0 to 40, it means your one kip is still not there. Your one kip is not there within the member DE because again, we are considering when x is from 0 to 40. So that is still on the left side. So if that's the case, okay, since we will be detaching this one, take a moment at D. Since again, of course, if you will detach, we will be exposing a vertical shear. There will be a shear. Okay, there will be a shear. There will be no moment, internal moment, but there will be a shear. Okay, so we cannot, I will not suggest using summation vertical. Instead, take a moment at D to cancel out that shear in this point D so that we will only expose the EB. Okay, so again, forget about this one kip that is not yet there, since again, that is on this left side yet. Okay, so one kip is still here. So, if now take a moment at D, what we'll be having is only the moment of your EB. Let's say counterclockwise is positive. So, the moment 20 times EB will be positive. And then, of course, calculating your EB, it will be useless or it will be 0. So, it means that when your load is within A to D, the segment A to D, then there is no EB. Your EB is 0. Now, considering your member DE still, focus is still on your member DE, but this time, your load is already within this span DE. So, it means your X is from 40, okay, 10 plus 10 plus 20 is 40. So, it means we are already on D to 60, it means up to your E. Okay, from 40 to 60, that is now another story or another equation, of course, since there will now be a new force that we will be considering on our free body diagram. So still, take a moment at D. However, there is now this one kip. Okay, take a moment at D. Counterclockwise is still positive, so 20 EB is still positive. However, there's a 1 kip multiplied that is counterclockwise. I mean that's going clockwise, so that is a negative since our counterclockwise is assumed to be positive. However, what is the moment arm of that? Since that is moving, of course, which has a distance x in reference to your A. So this is still x from A. So what we only need is the distance from your point of reference of the moment at D with your moment under consideration or force under consideration. So the moment arm will be what? This distance. So what is the distance? That will be x is from A to that force, so x, and then subtract this known distance, which is 40. So that will make it x minus 40. So again, that is the moment arm of your one kip with respect to your point D. Okay, so negative, since that is clockwise. So now, rearranging this one, you will have the equation of EB. EB is the response. Okay, your x is the position in terms of the distance or the position x. Okay, so response in terms or with respect, or that is a function of the distance x. So again, you will be having 2. Okay, when x is from 0 to 40, your EB is 0. But when x is from 40 to 60, there will be now a value of that, wherein that is x over 20 minus 2. Okay, so that's it. Now we have this equation of EB. We can actually proceed. Okay, proceed to your original figure, considering the whole structure. Okay, considering this whole structure here, we have already the equation of EB, or the value of EB. Then we can take a moment at A to cancel out this AB for us to bring out the CB, since that is what we need. Okay, that is the response that we need. So now take a moment at A of this whole structure. Okay, again we need to divide, since there are two equations here, with 0 to 40 and from 40 to 60. So let's start by, of course, establishing the relationship of the three by taking a moment at A. I mean these two. By taking a moment at A, okay, counterclockwise positive still. So CB times 20. Okay, CB times 20 positive, and then your EB will be 60. 60 times EB is still positive. And then your 1 will be multiplied by a distance x, that is exactly x, since we are referencing it to A, going clockwise, so that is opposite, so negative. So x times 1 is x. Now, rearranging this one, we need your CB. So this goes rearranged this way. And then your EB, all we need to do is substitute what we calculated a while ago. So we will be separating this into two equations. So when EB is 0, that is at x 0 to 40. So if EB is 0, that will be useless. Your CB will just be x over 20. And then at x equals 40 to 60, your EB will be this value. Substitute that one as a value of your EB. Okay, EB, plug it in. Simplify, you will have this new equation of CB, which is good when x is 40 to 60. This is when x is 0 to 40. Okay, so you might be confused. Sir, why is it that there are two values of 40? It means that if we want to get the value at 40 feet, then we will be using this or this equation. Okay, since we are considering a point D, a point or a single point, let's say 40, that is a point D. So that equation here is representing just before, okay, very close to the point D. Okay, so that is approximately 40, but we can actually just plug in a 40 value. Or that means that it's supposed to be 39.99999. And this value here is also just after, so that is 40.00001. Okay, to differentiate these two. Okay, the 40 here is referring to the left side, the effect of the 40 or the load at D on the left side, and then once it will surpass the point D, that is now the 40 feet in this equation. Okay, so now we have the response. We are good with the response equation. All we need to do is draw the equation, the graph of this. That will be the line graph, which will be our inference line. So now, okay, this is our two equation. So all we need to do is plot. Okay, so actually, in drawing the diagram, the length of the member or the structure under consideration for the load will be moving will be, of course, the length of your influence line diagram. Okay, so actually it is better for us to draw that one below the structure itself, especially if that is just a beam. Okay, so if we are going for us to project this one, okay, so that at the same time, if we are moving this one kip, we can actually locate down below the response of that. Okay, due to one kip only. So now, first is when x is 0 to 40, so it means from A to D. So all we need to do is plug in at A. If you want to know the value at A, x equals 0, isn't it? So if x is equal to 0 in this equation, that will be 0. So that will be 0. Actually, in plotting a line, you only need 2 points, isn't it? You only need 2 points to plot the line. If you want to verify, you can use 3 or more than. But actually, in a line, plotting a line, and how do you know that this is a line? Of course, first degree equations. So it means that it's just a straight line. And if you want to draw, or you only need a minimum, or yes, a minimum of 2 points to draw this one. So for me, I want to get the first point and the last point. So at x equals 0, that will be 0. At x equals 40, that is 40 divided by 20, it will be 2. So plotting that one, okay, that is the ordinate. That means that is the value of CV. That's the value of CV at when the load 1 kip is at 0. That is the value of CV when the 1 kip load is at point D, or at 40 meters. Okay, so that's it. We will try to connect that one with a straight line. Then actually you can use this line now to to investigate when that 1 kip is at a certain distance. For example, we want to calculate the CV when that is exactly at point B. All you need to do is project the distance. And then by ratio and proportion, you can calculate that to be 0.5. If you want to get the exact value, I mean the value of the response, when that is exactly on top of the support under consideration, then by using this line diagram, of course, ratio and proportion, that will be exactly 1, which is true. It will be carrying the entire, since that is on its top. Okay, the entire force. So that's it. That is the line influence line, or the line diagram of our equation if x is from 0 to 40. Now next is the remaining part when x is from 40 to 60. Okay, from 40 to 60. So plug in your 40 to the equation. So that is 40 divided by 10 is 4. Subtract that one from 6 will be 2. That's supposed to be, since that should be connected. Okay, so that is also 2. And then when 60 is your x, that will be 60 divided by 10 is 6. 6 minus 6 is 0. So it will be 0. Okay, why? Of course, because that will be received totally by the reaction at E. Okay, so it means this is the influence line of CV. Therefore, our next problem involving CV is to get the maximum response due to 50 kips. Okay, so the maximum response is the maximum vertical reaction at C. Is all you need to do is read the ordinate. Okay, read the ordinate. Where is the maximum? Of course, by merely looking at this, your maximum is 2. Okay, so the maximum is 2. And then all we need to do, that is the ordinate. Okay, ordinate using the unit load influence line. Multiply the actual load, which is 50. So 2 times 50, that will make it 100 kips. So it means that is the maximum reaction. Okay, that is the maximum reaction that CV will have with a 50 kip moving from A to E. Okay, and for you to predict where is the location of that, for us to have that maximum 100 kip, use the influence line that is located at this distance, which is exactly at D. Okay, which is exactly located at D. So it means that when load is at joint D, or that is x equals 40, you will have the maximum CV to be 100 kips. Okay, so that is the analysis using the influence line. Okay, so let's try to have one more. This time we will try to have no, we are not yet done, since we are still on A. We need to calculate the internal moment. Okay, so let's proceed with the internal moment. So internal moment, that is your MB. Okay, internal moment is MB. So if we will try to figure out that MB, we need to expose that one. So I will cut at B, expose. If you want, consider the right side, left side. For me, I want to consider the left side. Less complicated figure. So there will be 2 chances again for you to predict how many equations do I need to create is, of course, to analyze the scenario. So if I will cut that one at B, one scenario is that your 1 kip is within this left side that I am considering. And the other scenario is if that one keep will surpass, it will now be on the other side of the point B under consideration. So we will be having two equations when x equals when x is from 0 to 10, and then when x is from 10 to 60 up to your point A. So that's it. So how do we establish this one? Okay, actually we need first to calculate AB because a while ago we only established your EB and CB. Okay, so using this whole structure, summation vertical, so AB, CB, EB going up positive, minus 1, the load going down. And then of course, for us to calculate AB, simplify, 1 will go positive, CB and EB will go negative. And then all we need to do is substitute. However, if we will try to go there again, there are two values of EB and CB. When EB is, when x is 0 to 40, your EB is 0. And when that is 40 to 60, that is this value. And for your CB, the same thing. If x is 0 to 40, this is this value. 40 to 60, this is this value. However, for our case in AB, our cutoff is at 10. Okay? So, when AB is 0 to 40. Okay, so let's start with 0 to 40. When 0 to 40, yes, still. Okay, so first we are establishing AB. So when x is from 0 to 40, your values of EB is 0 and then your CB is simply x over 20. And simplify this one, therefore we will be having our AB will be 1 minus x over 20 when x is 0 to 40. And then change that one with the values of EB and CB when x is 40 to 60. So this is your EB this time, and then that is your CB this time. Simplify, you will have x over 20 minus 30. Okay, you can check this one by going back to our values. There you go, okay. And then now we have your AB. We only need this one. This is not what we care because we only be needing this one to solve for the MB. Because MB is what we need, what we will be drawing the inference line. So now, considering this now, cut at B. So expose, use the left side. So first scenario is when x is within this one, when the load is within this AB. So that is from 0 to 10. So summation moment at B. Okay, since if I will to take a moment at A, I need to know the shear, since there should be a shear, but I will not be drawing that one since I do not need that one. Okay, so for me to cancel out the effect of that shear here at point B, I will take a moment at B, so that I will have now the MB in terms of the value of AB, which we solved a while ago. So take a moment at B, counterclockwise positive. So MB, let's say that it's counterclockwise. Again, it's up to you to assume. Actually, if you assume the opposite way, that will reflect on the values of x. In the substitution of x. So it's up to you. Actually, you can consider it counterclockwise or clockwise, it doesn't matter. So, assuming a counterclockwise, okay, take a moment at B, counterclockwise positive, MB will be positive. However, your AB will be going clockwise, so negative AB times the moment arm 10, negative, and then your one keep is going counterclockwise also, so that is a positive. So 1 times the distance, this is 10 and that is x, so this distance moment arm to B is 10 minus x. And then simplifying, you will have exactly, okay, substitute your AB by the way, okay, substitute your AB, we need to substitute the AB, wherein your AB will be 10 minus x, since we are considering still from 0 to 10, so going back there, 0 to 10, the value of AB is within this range. Okay, that is 0 to 40. So we still, your 0 to 10 is using this 1 minus x over 20. Okay. This one. Okay. By the way, I just interchange. Since this will be going positive and this will be going negative. So this is your AB. 1 minus x over 20. Yeah. So now, all we need to do is simplify, okay, just simple algebra, that will be giving us x over 2. So that will be the equation of MB when x is 0 to 10. Now, let's move on. When load is now on the opposite side, so now we will not be having this one keeps. So we can now again still focus on your cut off. So this is now our figure here. There is no one keep already. So we will only be having, take a moment, again counterclockwise positive, MB is positive, your 10 AB will be negative, okay, it will go positive on the other side, and substitute your AB, but this time, there will be two chances, due to this cutoff here, 0 to 40, we actually need only from 0, the rest, 20 to 60. However, there is another cutoff here, due to the hinge. That will be giving us three equations of MB. Okay, first is when your one kip or your load is within the left side. Second, these two remaining is when that is on the right side, but that will be divided into two due to your hinge here. Okay, so again, so for us to target this 40, we will be using the rest. Again, we used a while ago the 0 to 10. So now, we will be using the 10 to 40. Okay, 10 to 40. 10 to 40. So, still, your AB will be this value. Okay, your AB will be this value. So now, simplifying, of course, simplifying that one, that will be 10 minus x over 2. And then now, let's move on to the last possibility when x is 40 to 60. Your AB will become substituted 1. X over 20 minus 30 minus 3, substituted 1, simplify, will have x over 2 minus 30. So we will be having three equations of this, this MB. It means we will be having three different lines to outline the entire effect of the variable load. Okay, so that's it. First is from 0 to 10. Okay, 0 to 10, we will be using this equation. 10 to 40, this equation. 40 to 60, this equation. So actually, these three equations are here. Okay, first is from 0 to 10. So if x is 0, of course that will be 0. If x is 10, that will be 10 divided by 2, 5. Positive. Okay, you need to consider, of course, this sign at the same time. Now, moving on to 10 to 40, So substitute 10 to this equation. That will be 10 divided by 2 is 5, so 10 minus 5 is 5, so that will be connected to the line a while ago. And then substitute 40, that will be 40 divided by 2, 20 minus 10 will be a negative 10. Okay, we will now be having a negative 10, connected one by a straight line, that is the influence line from B to D. And then finally, the third equation, if x is 40 to 60, that is D to E. So substitute 40, so 40 divided by 2 is 20 minus 30 is negative 10 still, so that will connect. And finally, 60, so 60 divided by 2 is 30 minus 30 will make it 0. So connecting these three lines, this and that, we will have your influence line, and then we will be using this influence line to locate the location of the maximum response, wherein the response we are analyzing is the internal moment at B. So, there are two possibilities, a maximum positive and maximum negative. If it says there maximum, the absolute maximum, then all we need to do is compare the maximum of the negative and positive. So that makes it negative 10. However, there is no specification if that's an absolute, so let's just take the maximum positive and then the maximum negative. Okay. First is the maximum positive, for if you will try to look at that, that is 5 and located exactly when the load is exactly at B itself, on top of the point under consideration. So for us to calculate the actual response, again, the ordinate of the unit load influence line, multiply the actual load 15. 5 times 50 will be 250, and that is a moment, so keep it. So that is when load is at joint B or x equals 10. And then second maximum, that is the maximum negative. So again, as you can see, this explains that when your one kip moves across C, okay, across your C, when that is still before your C, your moment at B is positive. It means that that is concaving upward. When the load is within this range, that will be bending upward. But once that one kip will now be surpassing your point C, this will now be the one curving upward. This will now be, since again, that explains a negative moment. Negative moment, again, concave downward, isn't it? It will be concaving downward. So when load is beyond C, this will now concave downward. It will now start to concave downward, and we will be having this maximum concavity or maximum moment negative when that is at joint D. Okay. So all you need to do is multiply the actual load to the negative 10, makes it negative 500, and that is when your load is exactly at joint D, or that is x equals 40. So that's it. Maximum response. Analyzing the structure, the maximum effect of the moving load or the variable load, okay, using the inference line. So that's it. So again, do not forget, the first step is first to assume a unit load, okay, to make your drawing general. Since again, look at this. If that is 50 kips, still you can use this inference line. If we will change that one to, let's say, 50.1 or 55 or 100, you can still use this one. All you need to do is change the multiplier of the ordinate. Okay, so that's it. Let's have one more. This time a frame. So draw the inference line for the vertical and moment reaction at A of the frame shown. So we will be analyzing, or we will be investigating the vertical reaction at A and then the moment reaction at A, since this is a fixed support due to, of course, a variable loading. Okay, so let's say the loading is moving within from B to D. We cannot imagine a load going up here. Okay, since that's a frame. So let's say that this is a part of let's say a building, or maybe that is a part of a bridge. So that is the frame itself. We cannot analyze. We cannot imagine a load going up. Is there a load going up from A to C? For example, this is an actual frame. You cannot imagine. So we can just assume that a load is passing from B to D, or moving from B to D. Okay. So that's it. First, again, is assume unit load. So let's say 1 kip, since we are, okay, there is no, we are still on feet. So maybe we will expect a load which is in feet, kip in feet, kip feet or inches. Okay, so 1 kip, let's say 1 kip. Okay, or again, if you are after a kilonewton, then use a 1 kilonewton. Okay. So establish a fixed point. Let's say that is point B. So that's where we will be recording the distance x. So let's start with the vertical reaction at A. Let's call that one as AB. So actually it is simple, since this is a determinate. So summate vertical, we can expose actually the value of AB. So summation vertical, taking a moment, taking summation vertical, going up positive, AB is positive, and the only going down is your 1. And that doesn't matter if your 1 is here on this side or on this side. Okay, so it means we will be having your AB to be constant. It is not affected by the location of that 1 kip. Your vertical reaction AB is not affected by the movement of your load 1 kip. Okay, so it will be constant. And then the second there is the moment at A. So let's call that one as M sub A. Take a moment at A for us to expose that one, MA. So that will be, let's say, counterclockwise positive. There will be 2 chances, right? Yes, 2 times. No, only 1. So it's either, okay, it's okay. You might be considering dividing this into 2. This will be on this side, which will be giving us a, what to call this one? A clockwise, counterclockwise, or this will be on the other side, which will be giving us clockwise. Actually, you can do that. However, analyzing the equation later on, the value of x or the location of that actually will be dictated by the value of x. So in case, for example, let's take a moment at A. So counterclockwise positive, your MA is positive. Let me first assume that that is here. So that will be a clockwise, will be a negative, and then the moment arm of that is x. This is x, but we only need this one, so x minus 6. So actually, you might be saying that this is only true. Simplifying, of course, MA is x minus 6. You might be saying that this is only true when x is from 6 to 18. But that will also be true. You can also use that equation from 0 to 6. Why? Because all we need to do, if this will be on the other side, is that it will become a clockwise. It will just change the negative to positive, which is true because if we will substitute an x which is less than 6, this will make the value inside a negative, it will be making it a positive. So this equation is general. It's either even if your load is within this side or in this side. So of course it is just simply analyzing of course the equation. But if you are not sure of that, you can actually divide. You can consider, let's say, from 0 to 6 and then from 6 to 18. Okay, but I'm explaining we can still use a single equation, since again the location of the left or right will be actually dictated by the sign of the value inside. Okay, if that is less than 6 or within this one, it will make it negative, so it will make the moment of that positive. So it's still good for this equation. So we'll be only having one equation for AB, one equation for MA. Okay, so simple as this. This is constant, so it means at any distance that is constant 1. So that is your influence line for AB. And then for MA, this is for actually dictated by the equation. So at x equals 0, substitute that will be a negative 6. At x, okay, evaluate exactly at C. Okay, exactly at C, actually that is on top of A. So 6, substitute 6 minus 6 is 0. And then at this point, actually we only need the first and the last, but all we need to do is of course use this one to check. So now at x equals 18, okay, at 18 is it yes, 18, yes, 18. So 6 plus 12 is 18, so at x equals 18, 18 minus 6 is 12, so this will be 12. Okay, so actually you can connect negative 6 to 12 directly, and actually that will pass is exactly as 0 here. You can prove that one by ratio proportion. So that's it. This is the influence line of your MA also. So if you want to get the maximum AB, okay, that will be maximum in any location. So meaning you can apply your load at any direction, your AB will remain the same, or at any position. And then of course your moment, that will be maximum negative. Okay, your moment here will be negative. It means negative. My assumption is counterclockwise, isn't it? So it means that will be going clockwise when your load is within this span BC. So that is true. When your one kip is within BC, that will be trying to rotate this frame, that will try to bend this frame counterclockwise, so that should be resisted by a clockwise moment at A. And then once that will be on the other side, it will be rotating the frame clockwise, so your reaction should be counterclockwise, which is actually explained by this influence line. So maximum there, if you want, again, there is no given load, so we will not be solving an actual response. But in case you're given a load, again, all you need to do is locate the point under consideration. Let's say you are analyzing the moment and the reaction when that load, let's say there's a 50 kip located at 10 feet. So all you need to do is locate the 10 feet. Locate the 10 feet in this line, or substitute 10 to the x in your equation. You will have your MA. Okay, you will have your MA ordinate of unit load. All you need to do is multiply the value of the actual load. Okay, so that's it. Influence line, application of influence line on beams and frames. Okay, so if you have any question, we will be discussing that one on the next live meeting, or you can comment that one on this discussion. Okay, so thank you very much for watching.